Welcome to the History of Women in Tech. My name is Sarah Dutkiewicz. I am part of the Greater Cleveland PC Users Group here in Cleveland, Ohio. So I want to thank Jim Evans for telling me about you guys. This is an exciting moment for me. So the History of Women in Tech, this talk actually originated over 15 years ago. Back when I was in college, I was wondering about where the women were in this industry. I was the only woman in a lot of my engineering courses, and the only female student and the only computer engineering student in my differential equations class. And I can remember looking around going, where are the other women? And so I ended up sitting in one of my labs, doing some searches online to see who was out there. And this talk has evolved from that. I mean, here we are now, like I said, just over 15 years later, and there are plenty of women from the past and today that we're going to talk about. So some of the women that we're going to talk about today include some pretty popular names if you've been in the industry a while. We'll talk about Ada Lovelace. We're going to talk about the ladies of the ENIAC. We're going to talk about Grace Murray Hopper, Barbara Liskov, Frances Allen, and Mary Lou Jepsen. So Ada Lovelace, her full name of course is Augusta Ada Byron Lady Lovelace. She was born in 1815, lived to 1852. She was the daughter of Lord Byron. That name, if you're familiar with poetry, he is the famous poet. But she was raised by her mother. She was raised by Lady Byron. Her mom had a lot of hopes of her daughter not becoming a poet. She did not want her daughter following in her dad's footsteps. It was just something mom was like, no way. So mom decided to make sure that Ada focused her studies in math and science. And in 1828, when Ada was just drawing around, she came up with this concept of what she called the flying machine. So 1828 was quite a long time ago, and so the flying machine, if you think about it nowadays, our flying machines are airplanes and drones and all sorts of other different flying devices. So it's cool to see that she had that kind of thought back then. Now, this whole not being able to follow in her father's footsteps, that didn't really sit well with her. She really wanted to go into poetry. So she asked her mom, she's like, Mom, if you can't give me poetry, can you give me poetical science? If you think about what we do in the tech fields in general, there is science to it. There is an art form to it, though, too. It's a creative outlet for those of us who understand what to do inside. So I can understand it getting a little bit on the poetical side, and definitely on the science side. And so with Ada, her mind was definitely math focused. That was her strong point, and of course, because her mom had her focus her studies on that, that's what it started with. But again, she was coming up with things like that flying machine. So it shows she had imagination. And then she was known for speaking in metaphors a lot. So her background in math, plus her wild imagination, plus her usage of metaphors, turned out to be this recipe for a magical experience. So this gentleman here, his name is Charles Babbage. He was Ada Lovelace's mentor. They met through Mary Somerville, who's a mathematician and astronomer, when Ada was 17 years old. So she got her start in the field fairly young. Her mentor, like her, was mathematically minded, so that really helped her. He also was a philosopher, an inventor, and a mechanical engineer. And what's nice is outside of working with Charles Babbage, which she worked with him for quite a long time, she also managed to have a life outside of work. She became the wife to the Earl of Lovelace. She was also a mom to 3 kids under 8. Now, being a parent myself, I have a 2.5-year-old and a 6-month-old, so I know how crazy it is juggling a tech career with children, but for her to do 3 kids under 8, I don't know how she did that. Now in 1843, she worked with Charles Babbage and came up with some predictions for the analytical engine. So some of her predictions for this analytical engine is that it could be used to compose complex music, it could be used to produce graphics, and that could also be used for practical and scientific use. Now let's think about that. This picture of this analytical engine, I mean, could you see something like that being able to compose music? Okay, there's a lot of computations going on there. I could see that possible. Produce graphics? How would we be displaying those? And then that practical and scientific use. I don't know if every home could have an analytical engine. I mean, could you picture having one of these in every room of your house? Probably not so much. So, I mean, Ada's vision back in 1843 was pretty phenomenal. A little absurd sounding, but still, if you think of where we are today, she was onto something. So here's the analytical engine in its whole entirety. What Ada did with the analytical engine is she documented Charles Babbage's work on it. And she also included what we call the first program. The first computer program ever to be documented, which was how to calculate a sequence of Bernoulli numbers with the analytical engine. So we see her as the first individual to conjure a computer algorithm. And in 1843, she published an English Science Journal on how codes can be created to handle letters, numbers, and symbols. Now, I don't know how many of you in our audience are programmers, but if you ever look at programming languages in general, they're codes, and they handle letters, numbers, and symbols. You've got your exclamation points, your question marks, your curly braces, your semicolons, your line numbers. You have all sorts of different things that make up your programming languages. But in 1843, Ada had already documented on how codes could be used to do that. Again, that's pretty cool to see a machine like this being able to do that. So some things that we can learn from Ada include follow your passion. So even though she really wanted to follow in her father's footsteps and go the poetic route, and her mom tried to derail that by going into the math and science route, her passion for science, but her poetical creativity led her to the success of where she ended up going. Another thing we can learn from Ada is that moms, we can work while maintaining a social life and a career. And that's some common topic among a lot of women in the industry, is finding that work-life balance. More pressure for moms just from a traditional role. And this is probably my favorite lesson from Ada, and that's choose a mentor who you're interested in learning from and that you can feed off of and feed into their energy. So as a person looking to work with a mentor, find somebody that you mesh with. Find somebody that you're interested in their work and that you're excited about their work, and then also let them play off of that excitement. Because you never know where that may lead. So that was Ada Lovelace. The next group of ladies we're going to talk about are the original ladies of the ENIAC. Now, if you take a look at these pictures, these are some of the photos that we've seen where the ladies are holding the various parts of the ENIAC. And so you can see things like, well, no, that's definitely not a PCI card. That's definitely not any of the other cards that we're familiar with. They're definitely much larger because the ENIAC itself was large. As you can see, it looks like it fills a room, and it does take up a lot of space. I got to see this back at the Smithsonian in 1999. Just a small portion of it filled a wall, and it was cool to see all the tubes and the knobs and the switches and how everything worked. It was just a piece of history that if it's still there, you catch it. But you can see just what it takes to program the ENIAC. Here's another picture of people working on the ENIAC. Again, it's filling up the whole room and then some. So the first of the ladies of the ENIAC that we're going to talk about is Kay Antonelli. So she was one of the 6 original programmers of the ENIAC. She's got a degree in mathematics. You're going to start seeing a pattern with these ladies in the ENIAC because Kay, she happened to have the joys of working with ballistics trajectories and landed into the ENIAC. And then from there, she eventually worked on the BINAC and UNIVAC 1 software design. And she also, interesting fact, would marry one of the ENIAC co-inventors. Now we look at Betty Jean Jennings Bartik. So this ENIAC, this huge computer, there was a part of it called the master programmer, and it was the central program of the ENIAC. And Betty Jean Jennings Bartik was one of the ladies responsible for administering the master programmer. And her job was to make it so it was easier to work with, and so it was able to handle more sophisticated problems. She too moved on to the BINAC and UNIVAC 1. Now Marlon Westkoff Meltzer, again one of the first group of the ENIAC programmers. She was actually hired originally for weather calculations, but after those weather calculations, she too moved on to ballistic trajectories. Like there was a war going on around that time. And then we have Frances Elizabeth Snyder-Holberton, also known as Betty. She's another one who got to work on the master programmer. Again, that's the central program for the ENIAC. She too moved on to UNIVAC 1. She also moved on to something called COBOL, which we'll talk about here later. And she worked on developing standards for FORTRAN. Frances Spence majored in math, minored in physics. Originally worked on ballistics trajectories. Was also one of the first ENIAC computer programmers. Ruth Teitelbaum, same kind of deal. She had a background in math. One of the first programmers. And she actually followed the ENIAC rather than going to the UNIVAC 1 and BINAC teams as we were seeing. Her job was to teach the next generation how to program the ENIAC, how to work with it. Now, Adele Goldstein, her background is a little bit different. So she was training some of those programmers on calculating those trajectories. But instead of being a programmer on the project, her job was to write the documentation for the ENIAC. Now, if you know anything with tech projects, it's documentation when it's there is crucial for both the business side and for the programmers, so that everybody knows what's going on. So it was good to see that back in 1946 that this documentation was done. As the screenshot shows, the documentation here was created in June 1st, 1946. And this is called the Report on the ENIAC. So in this picture here, you'll see that we're looking at 2 different ladies. One's Gloria Ruth Gordon Bolotsky, and the other's name is Esther Gertston. And they're both doing some programming on the ENIAC. So now let's think about computers that we have nowadays, keeping that in mind. Back in 1949, Popular Mechanics, which is a very popular magazine, no pun intended, they had said, where a calculator on the ENIAC is equipped with 18,000 vacuum tubes and weighs 30 tons, computers in the future may only have 1,000 vacuum tubes and perhaps weigh 1.5 tons. I don't know about you guys, but I sure don't want to be carrying a computer around that weighs 1.5 tons. First of all, I would need to find some kind of surgery to make me capable of carrying that amount. But second of all, that is huge. And if you take a look at that quote, I mean, we're a calculator on the ENIAC, so that's just a portion of the ENIAC. The ENIAC was a beast. So I could only imagine the ENIAC programmers today, if they saw the devices that we program on and how tiny they are and how light they are, it would be an amazing experience. Now this lady here, Admiral Grace Murray Hopper, she enjoyed tearing things apart to learn how they worked, which is pretty common in a techie's mindset, whether it's you're writing code or tearing apart hardware, tearing apart a network. We like to tear apart things, see how they work, and then put them together and see if they still work the way that we expect it. And she's got her background in math and physics. She began teaching in 1931. But in 1943, she decided that she should follow her family's traditions, and then she ended up joining the Navy. Within 6 months of joining the Navy, she was commissioned as a lieutenant. And this was one of the phrases she really did not like. We've always done it that way. It's just one of those phrases that if you think about it, if we've always done it the same way, we should always get the same results, or at least similar results. But is it something that you really want to be in? Do you really want to be in a holding pattern? Or do you want to be able to move forward? Do you want to be able to improve whatever you're trying to work on? In order to improve it, you have to challenge the we've always done it that way. You can't be afraid and let somebody say, oh, we can't do this because we've always done it this way. You do that and you're not necessarily going to find the ability to go forward. So Grace Murray Hopper anytime she heard that phrase, we've always done it that way, she would challenge it. She ended up having one amazing trail of success in her career. She started computing coefficients of arctangent with the Mark I. She created a 500-page manual of operations for the what they call the automatic sequence controlled calculator. And she eventually moved on to Mark II and Mark III. But that's not all. But wait, of course, there's more. So I mentioned, and I started with Grace Murray Hopper, that she liked to tear things apart and put them back together. She also wanted to bring this computer technology stuff to a much wider audience. Why should it just be for the science people? Why should it just be for the math-oriented people? She worked for various places. She worked from Harvard to Eckert-Mauchly to Remington Rand to Sperry Rand to UNIVAC. So she's went around not only just in the enterprises, but also in the military, also in education. She went through various industries, but she was on this, what I like to call the quest for programmer-friendly and application-friendly tools. So what does that mean? To me, that means that she wanted to make it so that it was a lot easier to work with. She happened to lead teams, and when she led teams, she promoted collaboration among the teams. And by promoting collaboration, this is some of the things she saw. She saw there were reduced errors because people were talking and figuring out where problems were and figuring out how to improve upon them a lot easier and ahead of finding more. It's less tedious. And then there's also less duplication of effort. So if you have, let's say we have 3 people on a project, we'll use these boxes as an example. We've got one box here, and we'll say they're working on one portion, another box may be working on another calculation, and this third team may be working on another. When they collaborate, they can all find out that maybe there's an overlap in their calculations, and set one person to write those calculations and work off of that, rather than having 3 people doing the same thing separately. She did a lot of work on the compiler as well. She showed that you could use mnemonics to transform them into binary code instructions. There was a series of computers called the AO series. It was the first that allowed the what they call call numbers to programming routines on magnetic tape. So then you could call those numbers to access the routine. But like I said, she didn't want to just keep it to the sciences. She didn't want to just keep it to the math-oriented people. She wanted to open the world through the development of programming languages. Now what you're seeing here on your screen is FLOW-MATIC code. Take a look at what we're looking at here. We've got, along the left-hand side, some numbers. If you're not familiar in programming, we call those things line numbers. But if you look at all the words, it's written in pretty much plain English. I mean, you're seeing things like input inventory file. Okay, compare a product. Okay, jump to operation B. I mean, write item C, read item. These are all written in plain English, but yet this is a programming language. This was something that Grace Murray Hopper worked on so that we could do something in English and not just for the techies. This language was used for automatic billing and payroll calculations. The UNIVAC 1 and UNIVAC 2 both understood 20 English statements, thanks to the FLOW-MATIC code. In 1952, Grace Murray Hopper published her first compiler paper. From FLOW-MATIC, she ended up working on COBOL. And as you can see, we've got numbers and more words that look fairly similar to English. I mean, we've got move, we've got end execution here, erase. I mean, these are all fairly English terms. It was greatly influenced by FLOW-MATIC. It was defined by the Council and their both their executive and short-range committees. And the first specs for COBOL appeared in 1959. Once those specs appeared, Grace Murray Hopper was one of the leaders for pushing to standardize COBOL. Some other features she worked on was language validation. She started in COBOL. Then she moved on to other programming languages, which also led to national and international standards for programming. More on Admiral Hopper. I'm spending a lot of time on her because her contributions are huge to the field. So in addition to working for companies, she also worked for the United States Naval Reserve. Her adventures, of course, are military, business, academia, private industry. She went across fields, so she didn't silo herself to one industry or one company. She retired from the business world in 1971. Retired's in double quotes for a reason, because with a lady with this much drive and this much knowledge and this goal to make technology more approachable to non-technical people, you know with that kind of energy that she's not going to slow down well. She continued to work well into her 80s. Here she is again. She was promoted to Commodore in 1983. 2 years later, when the titles merged, she became an admiral. In 1986, she retired from the Navy. And sadly, in 1992, she was buried with full naval honors. Some of the many awards that she's done. In 1969, she received the Computer Science Man of the Year Award from the Data Processing Management Association. Yes, I know it says Man of the Year, but when you're a female in a male-dominated field, you take what you get. If it's Man of the Year versus Woman of the Year, it really doesn't make that much of a difference to her. In 1971, company Sperry that she used to work for, they created an award in her name. In 1973, she became both the first American and the first woman Distinguished Fellow of the British Computer Society. And I could go on for days and days on Grace Murray Hopper's contributions to computing. She did a lot more than just the stuff I covered here today. These are just some of her other influences. As you can see, it's pretty much any form of programming, any little piece that's related to the language, she probably has had some influence in there. So some of the lessons we have from her include: just because we've always done it that way doesn't mean it's right. Don't be afraid to challenge those words. Something else that we found with her is that working as a team, it really works well, and especially when collaboration happens. Collaboration, communication goes a long way amongst multiple teams. And by bringing it down to plain English, computing is no longer just for the programmers and mathematicians. It's now more approachable by the non-technical people. So if we go back to that FLOW-MATIC programming language, talking to the business side, talking about their payroll stuff, I mean, we've got business people at this point coming into this. Not necessarily working on the home computer, but we're getting closer. Now, the next person we're going to talk about is Barbara Liskov. So in programming, we're familiar with this thing called the solid principle. That's what you're seeing on your screen at the moment, where S is single responsibility, O is open closed, L is Liskov's substitution, I is interface segregation, D is dependency inversion. So something that we use when we're writing our code. But that L, that Liskov substitution, that is attributed to Barbara Liskov. In 1968, she was the first woman to get her doctorate in computer science from Stanford. She worked with computer design and operating systems. She got her Turing Award for her work in languages. She created this computer called the Venus computer, which supported the construction of complex software, which supported up to what they called 16 teletypes. And these users connected to something called virtual machines. Now, if we think about this, this was a while back. We're not talking about the virtualization of today. So this is early days of virtualization. So to have it then, and to see where it is today, it's an amazing contribution. Now, she also worked on these things called CLU and Argus, two more programming languages that were featured in the communications of ACM. These were created by her group at MIT. CLU is known for modular programming, for data abstraction, polymorphism, whereas Argus was known for distributed applications and nested transactions. And you can see for this communications at ACM, the article that appears was called Distributed Programming in Argus. The publication date is March 1988. So other work that she's done include things such as database systems, specifically object-oriented database systems. She's also worked on garbage collection, caching, persistence, recovery, fault tolerance, security, geographic routing. So she's touched all sorts of different aspects of programming. And as the MIT president, Susan Hockfield, once said, that Barbara Liskov is revered in the MIT community for her role not only as a scholar, but also as a mentor and a leader. Her research has made her one of the world's leading authorities on computer language and system design. Now, Frances Allen, her work was on optimizing compilers and working in parallel, doing parallelization. She worked with the NSA on programming languages and security codes intelligence. In 1989, she became the first female IBM Fellow, and also became the first female IBM Academy President. In 2006, she received the AM Turing Award for improving programs and solving problems and accelerating the use of high-performance computing. So she's known for the high-performance thing. So if you're doing any like parallel processing, that's where her strong work is. It's in the parallelization and the compilers. She also published various works. So she worked with a gentleman named John Cook. So in 1966, she produced program optimization. In 1970, she was doing some more optimization work, but also doing some analysis. Again, more optimization in 1971, more analysis in 73 and 1974, more compiler optimization in 1976. Like I mentioned, Fran Allen's strong points were in the parallel world. If you're working with FORTRAN and have to do FORTRAN operations in parallel, you're using PTRAN. That's thanks to Frances Allen. She also did some new parallelism detection schemes. So working with parallel operations in FORTRAN, you owe her the credit on that. Now Mary Lou Jepsen. What I like about Mary Lou Jepsen's story is that her background isn't necessarily math. You've got some math and electrical engineering, but she also has this background in studio art. Her master's is in holography. Her PhD is in optical sciences. That's just an interesting combination, so to see where it leads, it's pretty neat. It makes sense. She became the head of the division, the display division over at the Google X Lab. She is also the founder of PixelChi, which is low-cost, low-powered LCD screens. And the big project that she's known for outside of her work with Google X stuff has been one laptop per child. There she is with the one laptop per child program. So what they've done is they've deployed laptops to children in over 50 other countries, more than 25 languages, and every child in Uruguay happens to have one of these laptops. The laptop has a sunlight readable display, and it's got ultra low power management system. So this makes it easy for them to work on their laptops wherever the environment that they're in. And that ultra low power management makes it easy for them to be able to work with their laptops for longer periods of time. And that XO laptop, it's the lowest power and most environmentally friendly laptop. You can see a lot of her work in various different things. Again, if we go back to her background with the studio art and the holography, and the electrical engineering, and the optical science, these start to make sense. And she went down the route talking of like head-mounted displays. So similar to what people know as Google Glass, something similar. She worked with HDTV stuff, projectors, holographic video systems, which with her background, this starts to make sense. And these are just a few of the women in tech that are out there or that have contributed. And some other ones that we need to talk about include Meg Whitman. Her name has been in the news quite often. She used to be with DreamWorks, she used to be with P&G, she used to be with Hasbro and eBay, and now she's with the artist currently known as HP. Padmasree Warrior, she's the CTO of Cisco and the former CTO of Motorola. So again, we're talking some pretty key players in the tech field, and their chief technology officer happens to be a woman. Anita Borg. So her story was she was bringing more non-technical women into the design side of things. She wanted to promote more women scientists and promote more growth in this field. And Anita Borg, what's nice about her is that not only did she work with creating a center to help promote this, but now the center is known in her name. Let me get a link for you guys. So the Anita Borg Institute, when you're doing research on women in tech, the Anita Borg Institute is the first place I always tell people to start. And I'm going to paste that link here in the chat channel. It's anitaborg.org. That way you can take a look and see just what her legacy is. And I say legacy because unfortunately she passed away with, I believe it was brain cancer. So she passed away young. She was in her early 50s when this happened. But her contributions are still well known. Ernest Schneider, she invented a computerized switching system for telephones. So not only are we talking about the programming language side, but we're also talking about the PC side, and we're talking about phones, because phones, they boil down to being computers as well. Jean Sammet, she worked on something called FLOW-MATIC, which is a programming language for symbolic manipulation of math formulas. And some other names you should probably take a look at include Maria Klaue over at Microsoft. I've pasted her name and her address in the chat channel. Should take a look more about Shafi Goldwasser. Lori Faith Craner. And Yoki Matsuoka. And these are just a few more people, a few more ladies in modern technology. They're still active today in promoting women in tech and advancing the field in general. So here I am now, over 15 years after sitting in my dorm room and wondering where are the women in tech. And I can see that there have been a lot of influential women here in our field. And with them, I learned a lot of lessons that have helped me to carry on in my own experiences. Some of the lessons that I've learned that I continue to carry forward and that I hope you've gathered from this presentation. With Ada and her experiences with Charles Babbage and his analytical engine, choose a mentor with who you're interested in learning from and that you're interested in feeding off of their excitement and energy for their project. And also be able to channel your excitement and feed it into their energy. It's a two-way road, that mentoring thing, and if you have the right mentor, you'll find that it can lead to success. With the ladies who worked on the ENIAC, the lesson I took from that was be open-minded with your career, because you never know where your adventures will take you. The ladies of the ENIAC, most of them started their career with ballistics trajectories, and then they just happened to fall into the ENIAC. And then from there, many of them moved on to UNIVAC and BINAC. You never know where that career is going to go. And for me, this one really hits close to home because, I mean, I have my bachelor's in computer science and engineering technology. When I graduated, I started in tech support, became a manager, moved from there into IT, doing database administration, system administration, desktop support. Then I moved on to being a developer for a few years. And now I'm an independent consultant with a focus on mentoring and training. If you told me this is where my career would have gone, I wouldn't believe it. But I kept an open mind. I mean, every day's an adventure. Let's see where it goes. With Grace Hopper, she had that whole strive to reach non-technical and business realms. Her lesson that I learned is make tech more approachable by translating it into plain English. I'm currently working with a software craftsmanship guild here in Akron. We're taking people through a 12-week boot camp to learn some programming from scratch, many of them with a non-technical background. And I always tell them, don't overthink. You've got a problem to solve, translate it into plain English. Write it down, draw pictures, But if you can't tell me the problem in plain English, we need to start at the very beginning and talking it through. Plain English is the language that the business understands. Plain English is the language that we as techies would also understand. Translate it first in English, and then it becomes more approachable, and a little less scary. Also through Grace Hopper, whenever you hear that people say, we've always done it that way, challenge it. If you want to improve processes, if you want to become more efficient at something, if you want to get better results quicker, you need to be able to, in order to get better and quicker, stop doing the same thing over and over. Because if you keep doing the same thing over and over, you're going to get the same results. Challenge, we've always done it that way so that you can become better, so that you can move forward. And these are just many of the women that I've found through my Women in Tech research. But this is just the beginning. I continue to do research on this topic. So if you're interested in learning more, I will give you my email address. And that's also in the chat channel. Are there any questions?
I'm not seeing anything yet, Sarah. But maybe since you've given them the opportunity, there may be. It doesn't look like it. Great presentation. Well, learned a lot.
Oh, thank you. Thank you.
There is somebody typing. Let's see what we get.
Yep, I see Judy's typing.
It was great to learn about how women have affected the tech industry. Good comment.
Thank you. Yeah,
and still are.
Yeah.
Absolutely. Anybody else have any questions while Judy's typing as well? We have a couple of minutes left.
Oh, absolutely. I see Judy's comment about this presentation should be used by high school history teachers when they're teaching about women in history. I mean, I can tell you as a student, I did not like my history courses at all. I couldn't find anything. To me, I was like, this is the stuff that happened in the past. But once I went into college and I started doing this, I was like, history isn't that bad of a thing after all. It's pretty cool. Be it not just women in tech, but tech in general.